We have been talking about El Nino mostly, but we have constantly mentioned the other zonal modes, the Indian Ocean dipole, Atlantic Nino. But if you know the tropical oceans, you know that there is this ITCZ, Intertropical Convergence Zone, running across all the oceans, has some complicated behavior in the Indian Ocean. Uh, Even in the other oceans, there is a piece that doesn't cross the equator with the sun, and the other pieces do, and so on. So you always wonder whether these tropical oceans are really independent, and if they are interacting, what are they doing? So there was this nice paper by a group of famous people who do El Nino a lot and other climate change topics as well. It's called Pan-Tropical Climate Interactions, which was a review of all the interactions and starts with this kind of a feedback figure, which is like a graphical summary, let's say, of the interactions. So pan-tropical feedbacks affecting ENSO. So coming back to El Nino Southern Oscillation, the black loop here represents internal Pacific fast positive feedbacks with the short arrows here, and delayed negative feedbacks with the long arrows. So there is a growing mode, and then there is a slower negative feedback modes, let's say. Interbasin feedbacks include Pacific feedbacks onto the Atlantic and Indian Oceans. They are shown in the blue arrows here. Um, and delayed negative feedbacks of the Atlantic and Indian Oceans onto the Pacific, shown in orange and green arrows. You can sit and look at them more carefully because I'm going to be brief as usual. And positive feedbacks of the Atlantic onto the Indian Ocean, shown in a yellow arrow here. So that's, you can see each one has a sign: positive here, negative here, positive, negative, negative, and so on. Are they all very well established? Well, we have papers showing that they work, but then there is also noise in the system, and the positive feedbacks of the Atlantic onto the Indian Ocean, and Indian Ocean has feedbacks onto the Pacific. So how do they all relate to each other? At what time scales? The effects of atmospheric noise forcing on the Pacific are indicated by the gray dotted arrow here, which is, you can think of it as the westerly wind bursts that we keep talking about. Let me make sure I'm in the frame here. I recorded, yeah, okay. Sorry, because I recorded something recently and my head was chopped off because I'm not very careful with these things. Nonetheless, here we are, fast time scale feedbacks here from SST to winds. You can think of the Bieknes feedbacks and winds back onto eastern thermocline through Kelvin waves and returning Rossby waves. So there are slower feedbacks from the mean thermocline onto the SST. You can think of those as seasonal to interannual variabilities, or even decadal variabilities, deeper thermocline versus shallower thermocline, and so on. And we have here the long-term negative feedback also from winds onto the mean thermocline. So you can think of that as the recharge-discharge process. And the SST wind feedbacks also is associated with the Pacific convection. So whether the La Nina is pushing the convection far west into the maritime continent region and Western Pacific, or relaxed winds are bringing it back. So there are positive feedbacks with the winds and SSTs in the Atlantic and Indian Oceans as well, because there are Walker cell components that are reaching out, and those SSTs in the Indian Ocean can have negative feedback on the winds of the Pacific. We have talked a little bit about. You can read more about it. And the wind SST feedbacks within these oceans, because they also have zonal modes of variability, Indian Ocean dipole and Atlantic Nino, and the Atlantic also has a negative feedback onto the Pacific, and there is a Indian Atlantic Ocean interaction. Are these all mutually exclusive or independent of each other? Not really. For example, you can think of the ITCZ being the connection in all of these things, remembering that the ITCZ, ITCZ splits in the Indian Ocean. The marine ITCZ pretty much remains south of the equator throughout the year because the Indian Ocean is warm, and in the summer months the ITCZ doesn't cross the equator like it just seems to transition and jump onto land, and the monsoon convergence zone is often called a CTZ or continental convergence zone. CTCZ, continental convergence zone, and so on. So basically, you know that there are feedbacks through the Walker cell and Hadley cell, and they are acting at different time scales. Just to jump around with the figures only and not going through the detailed text. Evolution of tropical interbasin interactions during a typical El Nino event. You can start here. So mean conditions, you have upwelling ITCZ and the warm SSTs here. The Atlantic Ocean has a warm pool and a cold tongue that's a bit different than here because of the Gulf of Guinea. I hope that's what this is. I always keep forgetting. Gulf of Mexico here pulls the ITCZ north as well. Warm pool which goes back and forth with the sun. Indian Ocean is warm, as we said. In the mean state, you see cooler temperatures here because of the Somali upwelling, but obviously that's a very seasonal feature. During the monsoon and intermonsoons and northeast monsoon, you have the changing circulations. So internal dynamics are shown here in the black arrows. Pacific to other basins are shown in the red arrows here that we talked about in the previous graphic summary. And you have Indian to Pacific feedbacks here. In terms of the westerly wind bursts, you can think of the MJOs coming in, and Pacific to Atlantic and back to Pacific feedbacks as well happening with the blue arrows, and you can see that they are phased here. JJA of year 0 of El Nino, so we are going from A to B, and you have El Nino starting like this year 2026 is showing warm SST anomalies already along the coast and in the cold tongue. So you have the Atlantic feedback apparently happening here already, and you have internal feedback. So you begin to have the movement of the warm pool, the reduced upwelling, warm SSTs, weaker trade winds, and Beckness feedback. And you have divergence. You can think of this as the Indo-Pacific tripole if you want, but of course we always try to separate the Indian Ocean dipole and the western half of the warmer part of the Indian Ocean dipole, or you can think of this as the Walker cell response on the Indian Ocean side. And this side, by September, October, November, you have internal dynamics working here as well. And when it is very strong, the Indian Ocean dipole, there are also Beckness feedbacks here and growing trade wind like southeasterly structures and northeasterly structures. Otherwise, you have the monsoon circulation. Internal dynamics continue here, so you can see the Walker cell perturbation, subsidence, drying, negative SST anomalies here. These patterns are changing because of global warming. You are seeing here warm SSTs during JJA of 0 as well. SON is showing stronger displacement, stronger sea surface temperatures here and here, stronger internal feedbacks on both sides, and the pieces of the Walker cell on either side. DJF, of course, is the peak El Nino, sending off waves all the way into the Arctic over to the Atlantic side. This is the Pacific North American pattern. There is also the North Pacific Oscillation, so various names, but you can see that the by DJF the IOD is basically dissipated away, and they have basin scale warming which continues typically into the following spring. So you go from DJF 0 to MAM 1, so you have again, shift of, remember the sun is to the south by DJF, so you have that effect showing up here. You can see these tilted lines, and you have convection over here, and you have changes in the basin-wide warming pattern here, which switches into JJA1. Sorry, the monsoon is getting set up, and there is a quasi-biennial time scale variability. The warming here tends to typically give a stronger monsoon following the El Nino year. During El Nino year, typically you have a weaker monsoon like we are having this year in 2026, and SON of the following year, you typically transition to a La Nina, and the internal feedbacks are beginning to recharge the system and push the warm pool back and set up the convection, the Walker Cell maritime continent, and the Indian Ocean response. Do they always happen this way? Not necessarily. There are lots of other feedbacks that are typical and common, but composites are always misleading because each El Nino looks different within the Pacific as well as in terms of feedbacks. Plus, the ITCZ here is very close to the equator, so it can start its own behavior in the Atlantic. It's very tilted. It's close to the equator on this side, far away from the equator on this side, and it touches the equator here routinely almost every year, which can send Kelvin waves, wind anomalies, and so-called Benguela Nino as well, which can be more to the south here as shown. You cannot, you don't see a warm anomaly, but you see a cold anomaly. But there is also a tropical version which we call the Atlantic Nino, and so on. So I'm being very brief, but I mentioned nearly all the feedbacks that are there that you can read. So Indo-Pacific Basin connection, when you have heating moving around, you have gill-type response, basically convergence at the surface and divergence at the top with waves associated with them, and monsoon is often portrayed as an off-equatorial heat source and a gill response as well, but obviously it has lots of non-linearities because gill is basically like a linear response in the tropical oceans to heatings. And you have the gill type, so this is the Indian Pacific Basin connection, this is the Atlantic and Pacific Basin connection. Again, gill type response here, or the Atlantic Ocean. You can see warm SSTs here, warm SSTs here. We are not talking about the seasons here, but you can see the perturbed Walker Cell sinking motion here going over the Indian Ocean into the Atlantic and coming from the other side as well. Okay, so shown on both sides here, the same thing, but you can see the transbasin variability index as 20-year trends. So this is trans-basin variability in degrees centigrade per year. It's some kind of a definition that you can look up. Are they all real? Basically, you can see there are correlations between Indo-Pacific SST anomalies showing this low frequency variability from the 1900s to 2015 or so. But there are also so-called regime shifts, and it's always a debate about whether more El Niños and fewer El Niños in decades make the mean state changes that look like regime shifts. And every time there is El Nino, there is a Walker Cell response and interbasin responses and feedbacks as well. Okay, so that's the 20th century reanalysis, winds from the Indo-Pacific, Pacific, and Pacific Tau X from ERA interim, and so two wind products are shown. You can see that there are differences. So this one is Pacific 20th century reconstruction is showing negative anomalies, which means stronger trade winds, depends on how you averaged it, but nonetheless you can see the correlations. Indo-Pacific from ERSST and PAC Tau X pre-1980s is minus 0.73 and post-1980 is minus 0.36. So there is kind of a regime shift in the relation. Atlantic and Pacific correlation with the Pacific zonal winds is minus 0.86 before 1980, but it drops to, increases to minus 0.94 for the post 1980. How the warming trends play into this is not obvious, but to the extent that these are 20-year averages, you can think that secular trends are conflated or confounded with them, but basically confirms that there are interbasin interactions at interannual timescales and low frequency timescales. And Clara Deser has other papers talking about Indo-Pacific teleconnections that also include extratropics in the Pacific and so on. Atlantic, because Pacific decadal oscillation, which is the extratropical mode, has a lot of impacts on the Indian Ocean, including on the cyclones and so on. Okay, so Atlantic Pacific basin connection with Indo-Pacific amplification. Another idea that this connection between the Atlantic and the Pacific are amplified by the Indo-Pacific interactions. So the enhanced Indo-Pacific Walker cell creates a divergence on this side which feeds into the Atlantic and amplifies the Atlantic Pacific basin interaction. So you can see here Pacific Ocean enhanced Ekman pumping. So if you have stronger trade winds and stronger upwelling, you are going to enhance the Ekman pumping or upwelling. You will crunch and make the warm pool warmer and convection stronger. The boiler box here gets about 5 meters of rain, so that upwelling here in the atmosphere or rising branch of the Walker cell here is going to get stronger, and divergence here is going to get stronger corresponding to warmer SSTs here. There are the subtropical signatures. This is showing depths here, so you have to be careful. So there is a depth signature here as well. There is a Indonesian through flow connection that many people talk about at these time scales, but oops, I screwed up something. But anyway, you get the idea. I just wanted to include it very briefly because the interactions between the three basins are always discussed, but no clear indication of exactly who is doing what, considering Pacific is the big monster occupying about 25% of the circumference in the deep tropics, and it has a ITCZ that is running across the whole extent of the Pacific and has so much convection, including the convection in the west. It is obviously doing a lot of things, and when the convection in the West Pacific moves, there are direct links in the ocean as well to the Eastern Pacific, which appears as El Nino. But that is also creating perturbations in the Indian and Atlantic Oceans, which also have a zonal mode, and El Nino peaks in December, January, February. IOD peaks in September, October, November, and Atlantic Nino peaks in June, July, August. So how are these phases related to each other, and what is the role of the ITCZ, and so on? These are not very easily answered, and it's not easy to separate them even in a fully coupled model. People do all kinds of experiments by suppressing the coupling or variability here and there, and you get some answers, but just remember that the relations are complicated, and there are in fact lots of feedbacks as we looked here. You can approximately do composites and say there are fast feedbacks, which we know surely as Bjerknes feedbacks, and there are slow feedbacks, recharge, discharge, and the thermocline, and there are fast and slow positive and negative responses within the Indian and Atlantic Oceans, and feedbacks between them, and feedbacks with the Pacific. I'm just going to leave it there. It doesn't help much, but it's useful to remember that the story is complicated. So when we look for simple answers to what El Nino does to the monsoon or the cyclones or the hurricanes, typhoons, and so on, there are too many other factors involved, so we have to be careful. Okay.